All right, let's talk about one of the most fundamental things that powers our entire world. It all kicks off with a really simple question that, honestly, you've probably never even stopped to think about. To figure that out, we have to zoom in. I mean, way in, down to the microscopic level of just a plain old metal wire. And what's happening in there is probably not what you'd expect. I want you to imagine the inside of that wire as a super busy highway. But it's a very strange highway. The things moving around aren't cars. They're these tiny, tiny particles called electrons. So in metals, the electrons on the very edge of the atoms aren't really attached to any one atom. They kind of form what scientists call a sea of electrons, just zipping around totally at random, bouncing between these fixed positive metal ions. It's pure chaos. But the moment you apply a voltage, say from a battery, that creates an electric field. And suddenly, all that chaos gets a purpose. All those electrons start drifting in one general direction. Okay, so now we've got this organized flow of charge. So the next logical question is, how do we measure it? How do we actually put a number on this movement? Well, that measurement is what we call electric current. The best way to think about it is to go back to our highway. Imagine you're standing on an overpass, and you're just counting how many cars pass a certain line on the road every minute. With electricity, we're basically doing the same thing. We're counting how much charge passes through a slice of the wire over a certain amount of time. And this brings us to a really simple but incredibly powerful formula. Current, which we represent with a capital I, is just the total amount of charge, that's delta Q, that flows past a point divided by the time it took for it to pass, which is delta T. It's that simple. More charge in less time, that means you've got a higher current. And the unit we use for this, you've probably heard of it. It's the ampere, or amp for short. So when you see a charger that's rated for, say, 1 amp, it literally means that 1 coulomb of charge, which is a mind-bogglingly huge number of electrons, is flowing through it every single second. Now, here's a little detail that's actually pretty fascinating. Even though we always talk about current having a direction, in the world of physics, it's technically what we call a scalar, not a vector. So why is that? Well, it's because the path is already set by the wire. The current can't just decide to go left or right. It has to follow the road it's on. And speaking of direction, we have to talk about this major historical, quirk. We know for a fact that it's the negatively charged electrons that are actually moving in the wire, right? They flow from the negative end of the battery to the positive one. But the scientists who first studied this stuff guessed wrong. They thought it was a flow of positive charge. So just by tradition, we still define the direction of current. We call it conventional current, as flowing from positive to negative. It's the exact opposite of what the electrons are doing, but it is the standard that every engineer and scientist uses today. Wild, right? So, knowing the total current is great for the big picture, but sometimes we need a much more detailed, almost microscopic view of what's happening with that flow. I mean, think about it. Is the flow of electrons perfectly even all the way across the wire? Or is it maybe more crowded in the middle, or maybe closer to the edges? To answer questions like that, we're going to need a new tool. And that new tool is called current density. We use the letter J for this one. Now, unlike the total current density is a true vector. It tells us two things: how much current is flowing through a tiny little spot inside the wire, and the exact direction of that flow at that precise point. It's really a measure of the flow's local intensity. Now, in simple situations where we can assume the flow is pretty uniform, the formula is just as straightforward. Current density J is just the total current I divided by the cross-sectional area of the wire A. It's all about how much flow is packed into a certain amount of space. So far, we've only been talking about our little electron friends as the things carrying the charge. But it turns out, depending on what material you're looking at, the vehicles on our charge highway can be totally different. And this is where it gets really interesting. So in metals, like we've seen, it's the free electrons doing all the work. Easy enough. But what about in electrolytes? Like the salt water inside a battery. It's actually two-way traffic. You have positive ions moving one way and negative ions moving the other way, and both of those flows add up to create the total current. And then you get to semiconductors, which are the heart of, everything electronic. It gets even more complex there. You have moving electrons, sure, but you also have these things called holes, which are basically just the absence of an electron, and these positively charged holes move around too, and also contribute to the current. So you might be wondering, okay, why do we need to know all this? The difference between current and current density, or what's carrying charge in a semiconductor? Well, because these are not just abstract ideas for physics class. So here's the bottom line. Understanding these concepts is literally the foundation of all modern technology. Electric current, I, gives us the big picture total flow. Current density, J, gives us the tiny local details you need to design, say, an intricate microchip. And knowing which particles are carrying the charge is what allows us to create everything from a car battery to the processor in your phone. And that brings me to one last, final puzzle for you to think about. The average speed of a single electron drifting in a wire, its drift speed, is incredibly, incredibly slow. Like slower than a snail. So if the electrons themselves are moving that slowly, how can a lamp on the other side of the room turn on the very instant you flip the switch? That's a good question for another time, but it really gets at the difference between the movement of a particle and the movement of the field that's pushing it.